Module 11, the cardiovascular system, cardiac muscle, and the cardiac cycle. If you remember learning about muscle types in a previous module, you know that cardiac muscle is unique from skeletal muscle and smooth muscle. But it does share characteristics of both of them. Like skeletal muscle, cardiac muscle is striated. And like smooth muscle, cardiac muscle is involuntary. You should be glad of that. Can you imagine needing to be conscious to control your heart beating continually, day in and day out? You wouldn't be able to sleep or it would stop beating. Well, cardiac muscle tissue is composed of long branching cells that for the most part have single nuclei. The cells are connected to each other by intercalcated discs, which conduct action potentials from each cell to the other. The heart itself is self-stimulatory, meaning it creates its own action potentials. It doesn't need an outside stimulus to contract, like skeletal muscle or smooth muscle. Now, the heart can be influenced by the parasympathetic and sympathetic divisions of the autonomic nervous system, but its primary stimulus isn't generated by the autonomic nervous system. What generates action potentials in the heart are special bundles of cardiac muscle tissue called nodes. There are two small nodes in the heart. The sinoatrial node is in the upper part of the right atrium, and the atrioventricular node is near the tricuspid valve in the right atrium. We sometimes refer to the sinoatrial node as the pacemaker of the heart because it is the location where action potentials are initiated for heartbeat. When the sinoatrial node generates action potentials, they move to both atria, signaling them to contract. Thus, the blood in the atria gets pushed into the ventricles. The action potentials of the atrial cells then stimulate an action potential in the atrioventricular node. It only takes a single second before the atrioventricular node then sends action potentials into the atrioventricular bundles. The AV bundles are special clusters of nodal tissue that extend through the interventricular septum, branching there as they fan out to each ventricle. These bundle fibers continue to branch into fine fibers called Purkinje fibers. The Purkinje fibers send action potentials to the cells of the ventricles so that they contract. The ventricular contraction then occurs after the atria have contracted and the ventricles are filled with blood. When the right ventricle contracts, blood flows into the pulmonary trunk. And when the left ventricle contracts, blood flows into the aorta. At the same time, the atrioventricular valves close so that blood won't flow back up to the atria. What makes the valves close? Well, any fluid will flow from an area of high pressure to an area of low pressure. When the muscles of the ventricles contract, the pressure in the ventricles increases. The blood in the ventricles pushes up against the cusps of the atrioventricular valves, and that causes them to close. Thus, the blood has nowhere else to travel except for the large vessels. When the ventricles relax again, the semilunar valves in the aorta and the pulmonary trunk close, so that blood won't flow backwards into the ventricles. They do this because of pressure too. You see, when the muscle tissue of the ventricles relaxes, the pressure in the ventricles reduces. The blood in the pulmonary trunk and the aorta pushes against the valves but gets caught in the cusps, forcing them to close. Additionally, when the ventricular pressure drops, the atrioventricular valves can open up again because now the atria are filled with blood and the pressure there is higher than the ventricles. The blood then starts to flow down into the ventricles even before the atria contract. This is called passive ventricular filling, and it results in filling the ventricles about 70% full. So when the atria do contract, they really just top off the blood transfer, adding the rest of the 30% to them. This complete cycle, beginning with spontaneous generation of action potentials of the sinoatrial node and ending with the emptying of the ventricles, is called the cardiac cycle. This cycle can be divided into two phases to better describe it. Systole, which literally means to contract, and diastole, which means to relax. So the systole phase is the phase of the cardiac cycle in which the ventricles contract. The diastole phase is the phase of the cardiac cycle in which the ventricles relax. And thus, the cardiac cycle is one complete round of diastole and systole. Have you ever had your blood pressure taken? When you do, you get a reading that has two numbers, something like 120/80. The first number in a blood pressure reading represents the systole pressure. That's the pressure that is in the aorta when the left ventricle contracts. Remember that is the systole phase. That's the highest pressure the aorta feels. The second number refers to the diastolic pressure, reflecting the minimum or lowest pressure the aorta feels. This is just before the ventricles contract and blood moves into the aorta. And of course, this happens during the diastolic phase. When you listen to a heartbeat, maybe with a stethoscope, you can hear it beat in a 2-beat rhythm. It kind of sounds like a lub-dub, 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 right? Have you ever wondered what makes that sound? After all, the muscle contraction doesn't make sound, or you'd be making beat sounds whenever you move your arms and legs. What you're hearing are the closing of the valves in the heart. When the ventricles contract, the atrioventricular valves close so blood doesn't back up into the atria. That's the louder lub sound. The dub is a shorter, softer sound made when the two smaller semilunar valves come together when they close.